Optical detectors. This is the topic for today's lecture. In optical communication system, we know that we need an optical signal, a light signal, and the light signal is generated by optical sources. The light generated by optical sources travels through cable, optical fiber optic cable, through core. Now, when the light signal is received at the receiving end, then we need to convert the light signal back into electrical signal. Because in any communication system, the natural signals, which are analog signals, say when we talk about an audio signal, so the audio signal will be converted into electrical, then electrical will be converted into light signal by the light sources, optical sources and transmitters. Now the light which will be converted into electrical by optical detectors, then we can use appropriate transducer to convert electrical signal into audio signal or voice signal. So this lecture is all about converting signal from light into electrical. So as we can see a diagram here, the radiation is coming, striking into a junction. This radiation can be seen here as a bundle of photons, which is actually light. So the optical detector, the input signal will be light, and the output signal, which you can see here in a green color, there is a current which is flowing in the circuit as a response to this light signal. E equal to h nu, the energy with which the photons are incident is h nu, where h is Planck's constant and nu is the frequency. So the devices which receive optical energy and convert into electrical energy are all optical detectors. Optical detectors or optical receivers. And those signals which are converted from light into electrical, and the electrical signal then can be used in telephone, in computer and other devices. Which needs the light signal back into the electrical form. So what is important here is the input is light and the output is electrical. The photons, the bundle of photons which are incident as a light signal, these photons help in exciting the carriers and then freeing some carriers and moving into the electrical circuit and constituting a current called as electrical current. So this is a diagram that includes both optical sources and optical detectors. In any optical communication system, there will be optical source, either LED or laser, popularly used as optical sources, light generators. We also can say optical transmitters. And then the light which is generated by optical sources. These lights, this light signal is subjected to optical path, which is fiber optic cable, and then it is received by optical detector, where the light signal is converted back into electrical signal. When we talk about optical parameters or optical detectors, there are some important parameters. When we talk about optical sources, there also we have discussed parameters, quantum efficiency, and quantum efficiency is the most important parameter there. That when you provide some electrical input, how many photons or how much light is generated is the quantum efficiency. Similarly, in analysis of optical detector as well, there are some important parameters like detector sensitivity, which is defined as the ratio of output current to input optical power, and it measures the efficiency of the device by assessing how much energy is lost. So it indicates how much energy is lost also, that can be assessed. It is simply because of, and if we compare this detector sensitivity with optical source parameters, we'll find there is the quantum efficiency where the input is electrical signal and the output is light. Here you see that is the ratio of output current to input optical power, because in optical detector the input is optical signal. So input is optical power, and how much output current is then being caused by the optical input power to the optical detector is indicated by the detector sensitivity. How sensitive it is means how much current flows per unit optical power which is given as the input. So in one way we can say efficiency, because efficiency is always calculated as output power divided by input power. So input is electrical power, output power which is proportional to current, more is the current, more is the power. So in one way it's assisting to, or it is indicating an efficiency term. And once we talk about efficiency, we know that when there is no 100% efficiency, which means the signal has been lost in the system. So this is how it is also used to evaluate, to determine the amount of energy which is lost. The complete optical energy is not converted into electrical, therefore there is some loss. If it is so, the efficiency will be 100%, which is not true. So this is first parameter called as detector sensitivity. Next is response time. Is the measure how quickly the detector can respond to the variations in the input light intensity. Response time means when there is, because the input is light signal, the light which is received by the optical detector may have varying values of intensity in it, and if the intensity or the brightness level of light which is incident is changing, varying accordingly, is there any change in the output signal, that is electrical output signal. So response time is how quickly means how much time it takes to respond to the variation or change in the input optical signal is the response time. Noise or interference is the third term which is produced in the device, maybe due to a number of factors. Interference is also unwanted signal. Noise is an unwanted signal. So how much noise is there in the system? How much noise is there? And accordingly, then we calculate SNR, signal to noise ratio. That depends on the value of noise. More is the noise, lesser will be the SNR value. So how much noise, how much interference has caused the system to degrade, has caused the signal to degrade the output is the third parameter. The next parameter is spectral response range. That is the range of wavelength or bandwidth over which device operates smoothly. It's not only device operates, but the device operates successfully, device operates smoothly. When the operation of device is very good, is well in a range of wavelength, that range is called as spectral response range. We can define the spectral response range in terms of wavelength as well as bandwidth. That what is the range of frequencies? Because see, we have once wavelength, we can easily calculate the frequency because we know the velocity of light. So we also can say that the range of wavelength means the range of bandwidth. What range of frequencies present in the signal is responding, is producing a significant output in the optical detector or at the receiving end. So this is another parameter. The next is gain. In the gain is the amount to which or amount by which the signal is amplified. How much amplification is taking place? How much signal strength has increased is evaluated by the factor or the parameter called as gain parameter. So if you look at here, the important parameters are detector sensitivity, response time, noise or interference, spectral response range, and the gain are the important parameters used in the analysis and performance evaluation of optical detectors. So now when we are discussing about photo detector or optical detector or optical receiver, we must not forget talking about photoelectric effect. Photoelectric effect is a fundamental principle, guiding principle in optical detector. As its name suggests, photoelectric, photon to electrical. What is photon? Light. So the effect that studies conversion from light signal into electrical is called as photoelectric effect. So the photoelectric effect is a fundamental principle that governs the optical detector or optical detection phenomenon. The phenomenon, the photoelectric phenomenon, it was observed by German scientist Hertz. We know the Hertz. This is the term used to denote the unit of frequency as well. So that Heinrich Hertz had observed this phenomenon. Then later Albert Einstein studied this effect and then quantified the discrete light energy. That how much light energy or how many photons are there which are converting into some amount of electrical current. So quantification, because the effect was observed by Hertz, then later quantification was made by Albert Einstein, and actually this is the important research and study for which the Nobel Prize was awarded to Einstein. Photoelectric effect is the main principle responsible for converting light signal into electrical signal. There are few examples: vacuum photodiodes, photomultipliers, which utilize this methodology in converting the light signal into electrical signal. The responsitivity is an important term used in photoelectric effect or in the discussion of optical detector. The responsitivity is the ratio of output electric current to the input optical power, which is expressed in ampere per watt. How much electrical power is given as the input, and then accordingly how much electrical current it is generating, that is indicated by the term called as responsivity. So this is photoelectric effect. Then this is the diagram where we can understand the light signal, the light arrays which are coming here as the input, and then the carriers electrons are excited and they are emitted, and here the electrons which are that much energy. Actually, suppose we talk about a PN junction. So in PN junction, what will happen? The light rays or the photons which are coming will provide energy, we can say bias to the PN junction, and then it will overcome the depletion layer, and then free carriers then will move into the circuit in the electrical circuit. So that's the electrical output. So this is a schematic highlighting photoelectric effect, which was observed by Hertz and then later quantified the analysis by Einstein, for which he was awarded Nobel Prize in 1921. So there are some observations when we discuss about the photoelectric effect. There are some important observations which include higher the brightness, higher the intensity, greater is the energy of electrons that are emitted from the surface. It's very simple. This is what we were talking about, responsivity. Responsivity, what does it indicate? How much electrical input power is given, accordingly how much current it generates or it emits the electrons. So if brightness increases, the intensity of light increases, obviously more light energy is falling on the surface or at the PN junction. So that will assist in releasing more number of electrons because of more energy. So more is the intensity, more is the brightness, more is the light energy, more is the light energy, greater will be the electrical current. Ultimately, electrical current. If more number of energy or more number of electrons are emitted and they are coming from the surface, which means more electrical current because of increased intensity of the light. So that's one observation. Second, a light wave of frequency should be able to knock off electrons provided a reasonable intensity is maintained. This is very important. If light falls or incident on the surface or at the PN junction or any optical detector, there is some minimum value of intensity below which no current will be resulted, after which, because that much light energy will be actually required to overcome the barrier, some barrier potential or some gap which is there in the material. So that much energy is indicating is equivalent to minimum light energy. So light intensity must be at more than some minimum value. If the incident light is of low intensity, say it's very low intensity, the metal surface must be continuously exposed for some time until enough waves strike the surface to knock off the electrons. Say when the intensity is very low, because we know that as far as the light energy is concerned, when you put some light energy on some surface and that too for a long time, the heating effect, the amount of that light energy, its intensity will increase. So that may cause emission of some electrons, but it does not mean that the low energy or low intensity light will suffice to provide enough amount of electrical current. Because if the light signal is incident and that too of low intensity for long time, then it may release some electrons. But after some time, again that effect will be lower, and when the effect is not there, then the current will not be significantly flowing. So what is important is there must be some minimum value of the signal which should be there, to emit the electrons. You can see here very clearly, this is a metal surface, low intensity light is coming. It is not doing anything, it's not affecting anything. As far as the carriers are there, they are not getting emitted. But as I mentioned in the previous slide, if the electrons are emitted, it means this radiation, this incident light is the surface is exposed to incident light for so long time. So therefore, it has enabled or it has released few electrons. So that's possible. If the intensity of light is very less, and if that low intensity light is incident for a long time, then it may excite some electrons. Otherwise, what is required? High intensity light or above some minimum value, because that minimum value will be the value at which no carriers are emitted. Once you cross that value, the the electrons are emitted. So it must be very high. The intensity value must be very high. So as I have mentioned that there are some standard devices like vacuum photodiode, then photodiode are popularly used as optical detectors. So what is vacuum photodiode? This is also called as phototube, vacuum tube actually, which consists of a cathode. You look at here, this is the structure where the current is coming here, right? And then uh, this is a tube structure and the electrons are here, light rays are incident here, and this is collecting anode. This side cathode from where the electrons are emitted, and since electrons are negative, so those electrons are attracted by the anode and then it is passed through this area constituting electrical current. So the material which is coated on cathode is photoemissive material. That material, the nature of the material is when the electrons, when the light waves, when the light signals, they strike on the surface which is coated with photoemissive material, then it will emit the electrons, and those electrons will be attracted by the collecting anode, and therefore they will be all focused to this area, and therefore those electrons will pass through this surface and then constitute an electrical current. Because see, initially there was no IC based or integrated circuit based diode or these type of photodiode. So initially it began with vacuum tube only, where there were anode and cathode, and the arrangement was made that the cathode was coated with such a material that can accelerate the emission of electrons when the light strikes on the surface. So when cathode detects the photons, electrons are emitted according to photoelectric effect, and the current will go through the circuit because the electrons are attracted by the anode. So this is working principle of vacuum tube photodiode or phototube. But there is a difficulty that it's physically it was too big. As I told you that the major limitation related to the vacuum tube photodiode is it's too big dimensionally, and it operates in a wavelength range lower than what fiber optic communication requires. As I mentioned in the beginning, that optical detectors, they are mainly needed in optical communication system where the signal was already transmitted in the form of light and we want to recover it. So in optical communication range, the wavelength range is different. Frequency range is very high, wavelength range is very low. So it's not that wavelength range which is used in optical communication supported by vacuum tubes. So that's a big challenge, and its dimension is size is so big. So it also involves much voltage to power it. Another thing that when you really want to power it, a lot of energy, a lot of voltage is required to excite the vacuum tube, to operate the vacuum tube. So energy consumption is very high. And the responsivity of vacuum photodiode is generally in the range of milliampere per watt, and that's very less. When you provide several watts of the energy, then it is producing hardly current in milliampere. So several watts of voltage, several watts of power, and that too producing a few milliampere of current, that's not very good in vacuum tube. So then the next one came as a photomultiplier, where you can see that there are some more electrodes which are introduced as diodes. You can say diodes mean dynamic anodes. You can say like that. The acceleration is done by these specific anodes. They are special purpose anodes. High voltage is generated here. Look at this point, and then radiative energy comes here. It strikes here. Then electron is emitted, and then at diode, what happens? That more and more number of electrons are emitted. In fact, the secondary electrons are emitted from the diode, and then more and more number of electrons will get accumulated, will be collected by the anode here, and then you can, the equivalent energy, that electrical energy will also increase. So this is a photomultiplier. Why it's called as photomultiplier? Because the electrons which are also emitted as secondary electrons at diode. So the photons are multiplying. What we can say is the photons which have equivalently converted as electrons, which have produced some electrons, and those electrons are getting multiplied. We call it as photomultiplier. So efficiency is more, and built-in gain mechanism system is there due to diode. It has built-in gain mechanism. Gain is increased due to diode. Rather, series of diodes are used, which are specific or special type of anodes called as accelerating anodes also, and they are used actually to accelerate the electrons and to also generate the secondary electrons at the diode. So the uh, emitted electrons are attracted by intermediate diodes. In the ordinary vacuum tube photodiode or vacuum tube or phototube, there was single anode and single cathode. So whatever rays or electrons are emitted by the cathode, they are collected by the anode. But here there are intermediate diodes which are used to collect, and the intermediate diodes, they have very high amount of voltage. Therefore, they have highly capable of accelerating the electrons. So it can be more than one electron gets emitted. As I've told you, secondary electrons are also emitted, and that is due to mainly high kinetic energy the electron does have. So high kinetic energy electrons do have, and they strike the dynamic electrode, that is diode, which are having it higher potential. So it's used to accelerate as well as a reason for to be a reason for uh, generating secondary electrons. So it's acting like photomultiplier. The gain at which the diode is about 5, and there are typically 5 to 10 diodes in each multiplier. So generally the gain factor in the diode is 5 or more, and we can use some 5 to 10 number of diodes. So you can imagine if the diode gain is 5 and we are using number of diodes is 10, so 10 into 5, that is 50. So whatever input strength is there in the electron with which it is striking the diode, so the series of the diode combination will enhance that electron at least 10 times or 50 times when the gain factor is 50. So when the gain is high, obviously the secondary electrons will also be produced. The photomultiplier tubes are high speed but not suitable for fiber optic, as vacuum tube was not used. Similarly, the photomultiplier is not very much suitable for optical communication as well. Then comes photodiode. We can say semiconductor photodiode, because in semiconductor photodiode, you can see here there is a PN junction, and ordinary PN junction. What happens that in between the PN junction there is a layer called as depletion layer or depletion region, where there are only immobile charge carriers. So what is important in PN diode, I'm sorry, photodiode, is if you look at the negative terminal of battery, which is connected with P type. So please remember, when photodiode operates in reverse bias, because you can say photodiode when operates in forward bias may act as ordinary diode, but when it acts as a reverse bias, right, then only it is used as the photodiode. So light strikes in the PN junction in the form of photons. You can say number of incident photons which are actually incident at that area only where the depletion region is there. Each photons, they have a lot of energy to free an electron, and the hole will be left behind. Whenever electron departs, whenever electron is emitted, in that place there will be vacancy called as hole. It will move towards anode while the electrons move towards cathode, and thus electrical current is produced. You see here that when this is coming here, right, and then this is the holes are coming towards cathode and the electrons are coming towards anode. So this constitutes, because the direction of hole and electron will be always opposite. So your holes which are coming here electrons which are coming towards the positive terminal of the battery. So this is constituting the flow of current as the current flowing in the PN, that is photodiode. The area between P region and N region, as highlighted in the previous diagram, is called as depletion region. And the depletion, what is the characteristic of depletion region? This is how you can construct the photodiode. This shows a constructional diagram where you can see there is a silicon dioxide mask this side and this side that actually is providing insulation between this P and N region, right? So this N region is your cathode, and this P region, here we have given we can insert some aluminum rod or some similar thing, and we can make it as anode. So silicon nitride coating is also given there, silicon nitride, and this provides insulation between these two regions. So that insulation that makes the depletion region in the PN junction. So the area which is between P and N region is called as depletion region, and that region depletion, since the majority charge carriers are depleted from that region. So the depletion region is always high resistance area, and therefore photons get absorbed there in the uh, depletion region. So when some photons hit the depletion region, current is generated, because they will be the reason for generating the electrons because of energy received from the light signal. The next one is pin diode. In pin diode, what is done, that between P and N, we do not put silicon dioxide material or some insulating material. Rather, there is an intrinsic region. The intrinsic region will have lesser resistance as compared to purely insulating material. So it enables the probability of photons directly being absorbed in this layer will be little more, because of the resistance will be less here in this case. The remaining step and the flow is same as what we have seen in the photodiode. So semiconductor photodiodes are typically made of silicon and germanium, and then silicon or germanium will have peak responsivity of 0.5 to 1 ampere per volt, which is much better than the vacuum tube. Versatile with optical wavelength ranging from 300 nanometer to 1700 nanometer. Generally, is the range of optical wavelength for this device. And the size of each semiconductor is similar to that of almost LED. LED is a light source, whereas the photodiode is the light detector. But the size is generally almost similar and can easily be soldered to printed circuit board. So we can easily implement in the printed circuit board form as well. Then comes avalanche photodiode. Avalanche is actually a process, right, which is used to emit a more number of carriers. So it's a mechanism in which, by applying a large voltage to electron hole pairs, that converted from photon, with a large number of electron hole pairs which are converted from photon, and then they collide with the atoms and knocking more electrons out of them. The constituting, the holes and electrons, they collide with the constituting atoms. You can say parent atoms, and this is how they release the energy, and that energy again helps to emit more number of carriers. So the new electrons can further collide with more atoms, and then this process keeps repeating, and this is how in the avalanche process we get huge amount of carriers that can flow in good speed in the electrical circuit, and that constitutes the electrical current. The gain of avalanche photodiode is in millions, like a photomultiplier. that varies from 10 to 100. It means the gain is very, very high. Therefore, the current becomes very high in case of avalanche photodiode. If a silicon pin diode has the responsivity of 0.5 ampere per watt, then a silicon APD, that is avalanche photodiode, responsivity will be 75 ampere per watt, assuming the gain is 150 or the same. Say if the gain is almost same for both the devices, PIN diode and the APD, that is avalanche photodiode, for almost same gain under which both the devices are operating. So the responsivity for same game, even same game, the responsivity is very high in case of APD as compared to pin diode. You can simply compare that the value of gain when the value of gain is maintained as 150, the responsivity is 0.5 ampere per watt in case of pin photodiode, whereas in APD the same has increased exponentially considerably to 75 ampere per watt. So both the PIN diode and APD are their ideal and they're used for optical transmission, where PIN is very less expensive also when it comes to expenses cost. The cost is less in PIN diode. For longer distance communication, weaker source signal, suppose there is a weak source signal or long distance communications to be used, APD is generally preferred because of APD has more sensitivity. Because we know that sensitivity is the ability to detect the weakest signal. So if there is a weak source signal, we know that the source has generated a weak signal. There we will go for APD so that due to its high, due to its large sensitivity, the gain provided to the weak, even weak signal will be high and it can be detected and amplified. And even for longer distance, in longer distance, what happens? That signal strength goes down. So in order to recover that, in order to detect if the signal strength loss is very high, so weak signals will be almost faded. So in order to recover that, high sensitive or highly sensitive device called as APD, APD is used. That is avalanche photodiode. So when we are choosing an ideal detector, it is important to consider a number of factors: wavelength, light source, optical fiber length, fiber type, and the fiber material by which the fiber has been manufactured. So there are a lot of factors which are responsible when or which are taken into consideration when we choose an optical detector for certain specific application. Then comes phototransistor. As its name suggests, photons will be the input. You see here, there are two amplifiers which we have shown here, common emitter and common collector. In common emitter, the electrons, the photons, which are, see here, this is the base and this is the collector. So at collector base junction, the photons are incident in both the cases, either in common collector or in common emitter. The photons are emitted at collector base junction, and then as we know in the transistor what happens, that this is a common emitter, the first one, where the input is given to base and the ground, that is electrical input, but here there is no input. So collector base junction is receiving light signal, so there will be current which we can see through the flowing through the collector, and we can see the output across load also. So in case of common emitter, we know the load which is across the collector, whereas in common collector, the load is across the emitter. Otherwise, if you compare the circuitry of common emitter and common collector, you will find similar. Even the input is given at the same junction, but the place of load changes, the position of load changes in the common emitter and common collector. But what is important here is in phototransistor, our phototransistor also has capability that when its common base CV junction is exposed to light, then the current flows through the either collector or you can also say emitter. Current flows there in the circuit, so we can get output if we want output voltage across the load. Load is the collector resistance for common emitter and emitter resistance for common collector. So across the load we'll get the output. It means that there is some current flowing in the transistor. And we also know that the transistor has inherent quality of having gain because it is called as an amplifier. So there is a large amount of current which is likely to be obtained in case of phototransistor. There is an excitation from outside in the form of light, and there is one more quality of transistor itself, that's gain providing device is an amplifier. So we get enough amount of electrical current across the or through the or across the load, and across the load we can get the electrical output. So let's summarize this lecture. This lecture is all about optical detector. We have introduced optical detector through this lecture. We know that optical detector is a device that will convert the light signal into electrical signal. There are devices like photodiode, avalanche photodiode, vacuum tube, phototube, and then phototransistor. These are actually mainly used as the optical detectors, which are used which are used to convert light signal into electrical signal, and that electrical signal, wherever it is required in an application, maybe a telephone line or maybe computer, that electrical signal is given to those devices. And finally, using some appropriate transducer, if it is a voice signal, you can convert into voice, or if it is text or some other signal, that accordingly that type of device will be used, a transducer will be used to convert the signal into original signal which was transmitted by the transmitter in optical communication system. So that's all for this lecture. Thank you.